In an automatic control system, a controller initiates a corrective action based on the difference between the signal it receives and the set point for a controlled variable. The various types of corrective actions that controllers can provide are called control modes. With two-position control, a signal from a controller causes a final control element to move from one extreme to another, such as from on to off, or from fully opened to fully closed. To see how two-position control works, let's look at an illustration of a sump pump arrangement. In this system, a pump draws water out of a pit or sump. A float with a rod is the sensing element in the system. The float rod has two collars, which serve as stops for a linkage that connects the rod to a switch. It's part of an electrical circuit that starts and stops the sump pump motor. If the level in the sump rises, the float also rises, and the lower collar on the float rod pushes up the linkage to turn the switch on. This starts the sump pump motor. As the pump draws water out, the level in the sump drops, and the float moves down. When the water reaches the minimum level, the upper collar pulls down on the switch linkage, shutting off the pump motor. Now, in a two-position control system, a certain amount of change can occur in the process without causing a control system response. This amount of change is called the dead zone. The dead zone in this system is controlled by the positions of the two float rod collars. The dead zone can be reduced by moving the two collars closer together. A smaller change in level will then turn the pump on or off. But even though the water will be maintained at a more constant level, the pump will turn on and off more frequently. And this overuse could damage the system's components. With proportional control, a controller's output signal is proportional to its input signal. In other words, if the input to a proportional controller changes by a given amount, the controller's output will also change by a given amount. To explain proportional control, we'll use this illustration of an automatic level control system. We'll say that a temporary disturbance decreases the demand for water from the tank and causes the water's level to briefly surge above its set point. As the water rises, a level-sensing float converts the change in level to mechanical motion. The motion is detected by a measuring element or transmitter and converted to a pneumatic signal representing the value of the higher water level. This signal is sent to the controlling element or controller. The controller measures the signal, compares the signal to set point, computes the difference between the two values, and produces a corrective output signal that's proportional to the input signal. The controller sends that signal to the final control element in the system, a control valve. The control valve responds by closing down to decrease the flow of water to the tank. However, because of process characteristics such as resistance, capacitance, and dead time, the level fluctuates before it finally returns to set point. We can tell more about how the temporary change in water level affected the system if we plot the control signals on a graph. On the graph, the scale on the far left is marked off in feet to indicate the water level in the tank. The next scale indicates the value of the input signal to the controller in pounds per square inch, or PSI. The scale on the right indicates the value of the output signal from the controller. It, too, is in pounds per square inch. The dashed horizontal line represents the set point for the water level. In this example, the set point is 3 feet, which is equivalent to a 9 PSI input signal to the controller and a 9 PSI output signal from the controller. In this case, it increased to 13 PSI. The output signal caused the control valve to close, decreasing the supply of water to the tank. As the level in the tank fell, the input and output signals decreased accordingly. However, the process characteristics that we mentioned caused the signals to go through several fluctuations or cycles before returning to set point. With a temporary disturbance, process conditions return to their original state. So a proportional control system can normally return the controlled variable to set point. But if a continual disturbance occurs, a proportional controller may not be able to restore original conditions. For example, this graph shows the input and output signals when an ongoing decrease in demand caused the level in the tank to rise. In this example, the control system brought the process back under control. But when it did, the level stayed higher than the original set point. That's because the input signal to the controller increased, then stayed high because of the continual disturbance. As a result, the proportional output signal stayed high as well. The higher steady-state value that resulted, that is, the higher level that's represented by the input signal, is called the control point. The difference between the variable's control point and its original set point is called offset. Offset occurs because a proportional controller produces only enough output to bring a process back under control during a continual disturbance. It may not produce enough output to overcome the disturbance and return the process variable to its original set point. In some processes, a proportional controller may not return a process variable to its original set point. In other words, the controller's action may result in offset. However, a controller adjustment can sometimes be made to change the amount of offset. This adjustment affects what is known as the proportional band, or PB. Proportional band is the amount of output change, or delta output, in relation to a given amount of input change, or delta input. The proportional band value is usually multiplied by 100% so that it can be expressed as a percentage. When a controller's input change and output change are equal, the relationship between the signals is 1-to-1, and the proportional band is 100%. This condition is called a 100% PB. The input and output signals on this graph show a 100% proportional band. Now, the signals on this graph show a proportional band that's less than 100%, otherwise known as a narrow proportional band. With a narrow proportional band, a small change in input to the controller produces a larger change in output. This relationship is equivalent to a 50% proportional band, since 1/2 times 100% equals 50%. With a narrow proportional band, control action is rapid, and the value of the controlled variable stays closer to set point. However, decreasing a proportional band setting increases the amount of cycling, which can overwork system components. Now, the signals on this graph show a proportional band that's greater than 100%. This type of proportional band is called a wide proportional band. With a wide proportional band, a large change in input to the controller produces a smaller change in output. The proportional band for this example is 200%. Since the output signal changes less than the input signal, a wide proportional band can minimize the amount of cycling in a system. However, there's more offset with a wide proportional band. Some manufacturers use the term gain when describing a proportional control adjustment. Gain is the inverse of proportional band, and it's expressed as a quantity rather than as a percent value. For example, a 1 psi change in input that produces a 2 psi change in output represents a 50% proportional band. But since gain is the inverse of proportional band, the relationship between the change in input and output is reversed. So the gain in this example is 2. In this topic, we examined two-position control and proportional control, and we looked at how those control modes work in an automatic control system. Now let's try some practice questions. Now, in a two-position control system, a certain amount of change can occur in the process without causing a control system response. This amount of change is called the dead zone. The input and output signals on this graph represent a proportional control system's response to a continual disturbance. Proportional band is the amount of output change, or delta output, in relation to a given amount of input change, or delta input. Not all control modes can return a controlled variable to set point after a process disturbance. However, reset control is designed to adjust the output of a proportional controller to help eliminate offset and restore original process conditions. Reset action responds to a controlled variable's deviation from set point by increasing or repeating the amount of proportional control until the variable returns to set point. Reset control doesn't exist without proportional control. In fact, it's actually proportional plus reset control, since it adds an additional corrective action to the proportional action. Also, reset control is sometimes called proportional plus integral, or PI control, because it's based on a mathematical function called integration. In any case, it's easier to understand how reset control works by looking at an example. In this arrangement, an automatic control system is used to maintain the level of water in a tank. The input signal from the transmitter to the controller represents the level of water. The output from the controller adjusts a control valve in the supply line to the tank. If a continual disturbance causes a decrease in the flow of water from the tank, the level in the tank rises, and the input signal to the controller changes to reflect the higher level. How do you suppose the controller responds to the change in level? The controller responds by signaling the control valve to close down. This reduces the flow of water to the tank and allows the level in the tank to gradually return to set point. We can get a better idea of how the system responded to the disturbance if we plot the input and output signals on a graph. We'll include a time scale on the graph to see more clearly how the control action works. During the first minute, the increase in water level caused the input signal to the controller to increase from 9 psi to 11 psi, which is a change of 2 psi. During the same 1-minute interval, a proportional-only controller with a 100% proportional band would have produced an output signal that matched the input signal. But the output signal from this controller includes proportional action plus reset action. And it increased to 13 psi, a change of 4 psi. What this means is that the reset part of the control action increased or repeated the 2 psi proportional action one time in 1 minute. This is sometimes described as 1 minute per repeat, or 1 MPR. As the level of water in the tank dropped, both signals decreased, then fluctuated briefly before returning to steady state. That's because the value of the controlled variable, represented by the input signal, returned to its original set point of 9 psi. In our example, a reset control action of 1 minute per repeat was able to return the controlled variable to set point. Often the amount of reset in a system can be adjusted. However, a reset that's too fast can cause a controller to overcorrect and cause the process variable to cycle out of control. In those cases, a slower reset may be needed. Rate control is a control feature that responds to the speed at which a variable deviates from set point. The faster the variable changes, the greater the amount of rate control action. Rate control is normally combined with proportional control, so it's often called proportional plus rate control. Also, it's sometimes called proportional plus derivative, or PD control. In any case, when a process disturbance causes the input signal to a rate controller to change, the controller measures the speed or rate at which the input is changing and produces an instant boost to the proportional output signal. In effect, this action tries to stop changes in the input as soon as they're detected. To get a better understanding of rate control, we'll use this automatic level control system in which rate control has been added to a proportional controller. We'll say that a continual disturbance causes a decrease in the flow of water from the tank, which in turn causes the level in the tank to rise. If we look at a graph of the control signals from the process, we see that the rate controller responds to the disturbance by producing an immediate boost in output. This boost minimizes the water level's deviation from set point. Then, a combination of rate control and proportional control stops the water level from changing and brings it down almost to set point. However, because rate control responds only during changes in the input, and because proportional control only provides a proportional output, there may be some offset in the process variable. In other words, as long as the level is at steady state, even with offset, the rate controller will not provide a correcting output. When a process requires a rapid control action that eliminates offset, a control mode known as proportional plus reset plus rate control may be used. It combines the precise response action of reset control with the fast response action of rate control. Proportional plus reset plus rate control is sometimes called PID control, P for proportional, I for integral, which is the same as reset, and D for derivative, which is the same as rate. One example of a process that requires PID control is the gas-fired oil heating furnace represented here. During operation, oil flows through a pipe in the furnace combustion chamber. Gas flows through a valve in another pipe to a burner. As the gas burns, part of the heat that's produced is transferred through the pipe to the oil. The controlled variable is the temperature of the oil leaving the furnace. A sensing device in the oil pipe provides oil temperature readings to a temperature transmitter. The transmitter measures the temperature and provides a corresponding pneumatic signal to a controller. The controller uses that information to produce an output signal, which adjusts the control valve to regulate the furnace flame. Since the flow of oil through the pipe is reduced, there's more time for the oil to absorb heat, and its temperature increases. The control system responds by sending a larger signal to close down the control valve. This reduces the gas flow to the burner and decreases the amount of flame. As a result, less heat is transferred to the oil, and the oil temperature returns to set point. We can get a better idea of how the control system responded to the change in oil temperature by looking at the controller's input and output signals on this graph. The input signal to the controller represents the oil temperature. As the graph shows, when the temperature of the oil first began to increase, the controller immediately produced a corrective output signal that reflected the rate of change. This boost of control action stopped the temperature from changing as rapidly as it would have without rate action. As the rate portion of the controller output worked to stabilize the oil temperature, the reset portion of the output worked to return the oil temperature to set point. Soon, the combination of reset and rate control returned the oil temperature to steady state at its original set point. The final output signal also returned to steady state, but at a higher value. The higher output closed the control valve to a new setting to maintain the oil temperature at set point. In this topic, we described how reset control, rate control, and a combination of the two work in an automatic control system. Now let's try some practice questions. Not all control modes can return a controlled variable to set point after a process disturbance. However, reset control is designed to adjust the output of a proportional controller to help eliminate offset and restore original process conditions. Rate control is a control feature that responds to the speed at which a variable deviates from set point. The faster the variable changes, the greater the amount of rate control action. This graph shows the input and output signals for a control system that uses proportional plus reset plus rate, or PID control. In process systems, physical conditions such as pressure, temperature, level, and flow are subject to change. These changeable conditions are called process variables. To help maintain the efficiency of a process, the values of these variables are often controlled by automatic process control systems. Part of an operator's responsibility is to use these control systems and understand how they work. Many plant processes are monitored and regulated by some type of process control system. A process control system monitors the value of a process variable and provides actions that control the value of the variable. Two basic types of process control are manual control and automatic control. With manual control, an operator monitors the value of a process variable and then manually makes whatever adjustments are necessary to control the process. Automatic control is basically a form of control that's performed with little or no human intervention. To get a better understanding of how an automatic control system works, we'll use this simplified illustration of a system that's used to control the level of water in a tank. Since the level of the water is what's maintained at a desired value, it can be thought of as the controlled variable in the system. It can also be thought of as the measured variable, because the control system uses it as a basis for making operating changes. The level of the water will remain constant as long as the flow of water into the tank equals the flow of water out of the tank. In this system, the water level is controlled by regulating the flow of water into the tank. For that reason, the flow of water into the tank is called the manipulated variable. As with all automatic control systems, this system has four basic parts or elements. One element, the primary element, is a sensing device that's located where the process variable is monitored. In this system, the primary element is a float that senses the level of water in the tank. The float is connected through a mechanical linkage to the second element in the system, a measuring element. In this system, the measuring element is a transmitter. The transmitter detects the position of the float and transmits a signal representing the level in the tank to the third element in the system, a controlling element. The controlling element, or controller, measures the signal from the transmitter, compares the signal to the desired level setting, computes any difference between the two values, and if necessary, produces a corrective signal. The controller sends the corrective signal to the final control element, which in this case is a control valve. The control valve adjusts the flow of water to the tank as needed to keep the level at the desired setting. When a process is operating normally, the variables for that process will be at or near their desired values. The desired value of a process variable is known as the set point. For example, the set point for the water level in this system is 3 feet. When the values of the process variables in a system remain relatively constant over a period of time, the system is said to be operating under steady-state conditions. Most control systems will allow slight variations in the values of process variables. But if the value of a variable changes significantly from its set point, corrective action may be needed to return the process to its original operating conditions. To see how a process disturbance can affect a control system, let's look at the automatic level control system that we saw earlier. In this example, a process disturbance causes a decrease in the demand for water from the tank. The decrease in demand causes the level of water and the float to rise. In this case, the water level rises to 4 feet. The movement of the float is transferred through the mechanical linkage to the transmitter. The transmitter then sends a signal that's proportional to the increased water level to the controller. When the controller receives the signal, it measures the signal, compares the measured value to set point, and computes the difference between the two values. The controller then sends a corrective signal to the control valve. The control valve responds to the signal from the controller by closing to reduce the flow of water to the tank. This compensates for the decrease in demand that caused the water level to rise. As a result, the level returns to its original set point value of 3 feet. The transmitter is the measuring element in this system. It detects the position of the float and transmits a signal representing the level to the controlling element. One of the basic methods of control used by automatic process control systems is feedback control. In a feedback control system, a control action is initiated after the controlled variable has deviated from set point. To see how an automatic feedback control system works, we'll use this illustration of a heat exchange process. In this system, steam is used to heat water. The steam enters the system through a valve, then flows through tubes inside the heater, and exits the heater through a pipe on the other side. The steam transfers heat to the water, which enters the heater at the top, flows around the tubes, and exits the heater at the bottom. The temperature of the water at the outlet of the heater is the controlled variable for the system. It's also the measured variable, because the control system uses it as a basis for making operating changes. The manipulated variable in this system is the inlet steam flow. That is, the steam flow to the heater. It's adjusted to keep the outlet water temperature at set point. The primary element in this feedback control system is a temperature sensing device in the outlet water line. More specifically, the device is a temperature sensing bulb, which contains a gas. If the temperature of the water leaving the heater increases, the gas in the bulb expands. This causes a pressure increase that's carried along the tubing connecting the bulb to a temperature transmitter. The transmitter sends a pneumatic signal that's proportional to the water temperature to a controller. The controller measures the signal and compares it to set point. This is how the controller detects that the temperature of the water has increased. The controller then computes the difference between the temperature of the water and set point and sends a corrective signal to the final control element in the system, which is the control valve. The control valve responds to the signal from the controller by closing to reduce the amount of steam flow to the heater. As a result, less heat transfer takes place in the heater, and the outlet water temperature returns to set point. A feed-forward control system attempts to correct for a process disturbance before the controlled variable in the process deviates from set point. To get a better understanding of how a feed-forward control system works, let's look at an illustration of a heat exchange process that's controlled by a feed-forward system. In this system, steam flows through tubes inside a heater and heats water that flows around the tubes. The controlled variable in the system is the water temperature at the outlet of the heater. The inlet water temperature is used to determine whether a control action is needed to maintain the outlet water temperature. So it's the measured variable in the system. The manipulated variable, that is, the variable that's adjusted to maintain the outlet water temperature, is the steam flow into the heater. The feed-forward control system works like this. If the temperature of the water entering the heater changes, the primary element in the system, in this case, a temperature-sensing bulb, detects the change in temperature and changes the signal that it sends to a transmitter. The transmitter measures the signal from the temperature-sensing bulb and sends a proportional signal to a controller. The controller measures the signal from the transmitter and compares it to set point. If there's a difference between the two values, the controller sends a signal to the final control element in the system, the control valve. The control valve responds by opening or closing to change the amount of steam flow to the heater. If the temperature of the water flowing to the heater decreases, the control system opens the control valve to increase the steam flow to the heater. This provides more heat for transfer to the water and prevents the outlet water temperature from dropping below its desired value. Now, if the temperature of the water entering the heater increases, the control system closes the control valve to allow less steam to enter the heater. As a result, less heat is transferred to the water, and the outlet water temperature is kept from rising above its desired value. A feed-forward control system can be effective at correcting for certain process disturbances before the disturbance affects the controlled variable in the process. However, there are many possible disturbances in a process, and a typical feed-forward control system may not be able to respond to every one of them. For example, the feed-forward control system that we just looked at responds only to changes in the temperature of the water entering the heater. Other disturbances, such as a change in the pressure or temperature of the steam entering the heater, can also affect the outlet water temperature, but those disturbances will go unnoticed by the feed-forward control system. To correct for those types of disturbances, a combination of feedback and feed-forward control could be used. With combined control, the feed-forward part of the system responds to changes in the inlet water temperature, while the feedback part responds to changes in the outlet water temperature caused by other disturbances. By combining the features of feedback and feed-forward control, greater control over disturbances upstream of the process and within the process can be attained. In this topic, we saw how the four elements of an automatic control system work together to control a process, and how a control system responds to a process disturbance. We also saw how feedback control, feed-forward control, and a combination of the two methods work to control a process. Now let's try some practice questions related to this material. Right. The controlling element, or controller, computes the difference between the measured level and set point, and sends a corrective signal to the final control element. No, the controlling element, or controller, computes the difference between the measured level and set point, and sends a corrective signal to the final control element. The controlling element, or controller, measures the signal from the transmitter, compares the signal to the desired level setting, computes any difference between the two values, and if necessary, produces a corrective signal. The controller sends the corrective signal to the final control element, which in this case is a control valve. One of the basic methods of control used by automatic process control systems is feedback control. In a feedback control system, a control action is initiated after the controlled variable has deviated. A feed-forward control system attempts to correct for a process disturbance before the controlled variable in the process deviates from set point. All processes have characteristics that can affect how a control system responds to operating changes. Two of the more important of these characteristics are resistance and capacitance. Resistance can be thought of as an opposition to flow. Capacitance can be thought of as the ability to store energy. While these terms are commonly used in describing electrical circuits, they can also be applied to process systems that contain fluids. For example, in this system, the resistance is caused primarily by a valve that opposes the flow of liquid from a container. The system's capacitance, or ability to store energy, is determined by the size of the container. These same characteristics can also be applied to gas or vapor systems. For example, in this system, the resistance is caused primarily by a valve that opposes the flow of gas from a pressurized cylinder. The capacitance depends on the storage capacity of the cylinder. Now, in a thermal process, that is, one involving heat, resistance and capacitance may be somewhat different. Here, a flame is used to heat a beaker of liquid. In this arrangement, the wall of the beaker represents the resistance, since it resists the transfer of heat from the flame to the liquid. The amount of heat or thermal energy that the liquid is able to store represents the capacitance of the system. Process characteristics such as resistance and capacitance can affect how a control system responds to process disturbances. We can get a better understanding of how these characteristics can affect a system by looking at an illustration of a simple heat exchange process. In this system, steam flows through tubes in a heater and heats water that flows around the tubes. At the moment, the temperature of the steam entering the heater is 400 degrees Fahrenheit, and the temperature of the water leaving the heater is 200 degrees Fahrenheit. Now, suppose a process disturbance causes the temperature of the steam to suddenly rise to 500 degrees. What do you suppose will happen to the temperature of the water? Even though the steam temperature increased suddenly, the water temperature will remain unchanged briefly, then increase slowly. It's easier to see how the water temperature changes by plotting the temperature changes on a graph. On the graph, the vertical axis represents temperature, and the horizontal axis represents time. When we plot the steam temperature, we see the sudden increase from 400 degrees to 500 degrees. This type of disturbance is commonly called a step input or a step change. When we plot the water temperature, we see that there's a delay between when the steam temperature increased and when the water temperature first started to rise. This delay is called dead time. It can be thought of as the amount of time required to transfer energy from one point to another. In the heater, the transfer of heat from the steam to the water was delayed because of resistance to heat transfer through the tubes, and because of the water's capacitance, or the ability of the water to store heat. Another factor that can contribute to dead time is the distance that the heat has to travel to reach the temperature gauge. In this case, the greater the distance from the heater to the gauge, the greater the dead time. Looking back at the graph, we see that after the time delay, the water temperature gradually rose to a new value of 300 degrees. The total amount of time that passed from when the steam temperature changed until the water temperature reached its maximum amount of change is called lag time, or lag. Lag is caused by the combined effects of dead time and other process characteristics, such as resistance and capacitance. In this topic, we focused on certain characteristics of a process that can affect a control system's response to a process disturbance. Now let's try some practice questions that relate to this material. All processes have characteristics that can affect how a control system responds to operating changes. Two of the more important of these characteristics are resistance and capacitance. Resistance can be thought of as an opposition to flow. Capacitance can be thought of as the ability to store energy. While these terms are commonly used in describing electrical circuits, they can also be applied to process systems that contain fluids. The total amount of time that passed from when the steam temperature changed until the water temperature reached its maximum amount of change is called lag time, or lag. Lag is caused by the combined effects of dead time and other process characteristics, such as resistance and capacitance. In this arrangement, an automatic control system is used to maintain the level of water in a tank. If the level in the tank rises, what is the controller most likely to do? In this system, steam flows through tubes inside a heater and heats water that flows around the tubes. If the temperature of the water at the outlet of the heater is the controlled variable for the system, what is the measured variable? This feedback control system is used to maintain the outlet water temperature at set point. What will the control system do if an increase in inlet water temperature causes the outlet water temperature to rise? This feed-forward control system is used to maintain the temperature of the water flowing out of a heater. Based on the configuration of the system, what variable is measured to determine whether a control action is necessary? This feed-forward control system is used to maintain the temperature of the water flowing out of a heater. What will the control system do if the temperature of the water entering the heater decreases? In this process, the temperature of the water leaving the heater is controlled by a combined feedback and feed-forward control system. What is most likely to happen if there is an increase in the temperature of the water entering? In this example of heat transfer, a flame is used to heat a beaker of. In this heat exchanger, steam flows through tubes and heats water that flows around the tubes. If the temperature of the steam entering the heater suddenly increases, what will happen to the temperature of the water leaving the heater? In this system, steam flows through tubes inside a heater and heats water that flows around the tubes. If the temperature of the water at the outlet of the heater is the controlled variable for the system, what is the manipulated variable? This feed-forward control system is used to maintain the temperature of the water flowing out of a heater. Based on the configuration of the system, what variable is adjusted to keep the outlet water temperature at set point? This feed-forward control system is used to maintain the temperature of the water flowing out of a heater. What will the control system do if the temperature of the steam entering the heater decreases? In this process, the temperature of the water leaving the heater is controlled by a combined feedback and feed-forward control system. What is most likely to happen if there is an increase in the temperature of the steam entering the heater? In this example of heat transfer, a flame is used to heat a beaker of.